Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over problem number 26 on our epic collection of math induction proofs. We're going to be taking a look at the proof that 2 plus 4 plus 6 plus 2n is equal to n times the quantity n+1 for all positive integers n. Don't forget there are tons of examples in the description below, or you can just scan the QR code. And don't forget to help support our channel by subscribing, liking, and posting comments in the comment section. Alright, so let's go ahead and write down the question that we're going to be working on. Problem 26. So we have to prove the following statement. We have to prove the statement S sub n, which is that 2 plus 4 plus 6 plus continuously all the way to 2n is equal to n times the quantity n+1 for all positive integers n. Positive integer n. Another way you can say this same remark is n in the set of natural numbers. Alright? Okay. So let's go ahead and do it. Before we get started, let's go over the procedure for carrying out the mathematical induction proof. So we'll always start with the base case or anchor step. In that particular case, we show that S sub 1 is true. Alright, so something that you want to keep in mind is that in this particular case, n is the set of all positive integers, so it starts from 1. But in some problems, the base case is not necessarily 1. It could be higher, okay? And then secondly, you have the inductive hypothesis. We assume that S sub k is true. And then the third step is the inductive step, where we're going to use our assumption in step 2 to show that S sub k plus 1 is also true. Alright, so we have that domino effect happening. So in that situation, if we can show 3, then we have accomplished our goal of showing that the statement holds for all positive integers, and then we indicate what our conclusion is, which is a restatement of the original statement as being true. Alright, okay, let's do this. So first, we're going to start with the base case. So for the base case, or our anchor step, we are going to show that S sub 1 is true. Basically, we're setting n equal to 1. Okay? Alright, so let's do that. So we're looking at n equals 1. So when n is equal to 1, our statement S sub n becomes S sub 1. Okay, you see the statement that we're proving up here? See the subscript is n. So in n sub 1, when n equals 1, it becomes S sub 1. Okay? So S sub 1, you can either look at it two ways. It's either the first value or what you get when you substitute 1 into the formula. Alright? So you can plug in 1 here and do 2 times 1, or you can just take the first one. So let's take the first one, which is 2, the first term, which has been calculated for us. The question is this equal to? We don't know yet. We have to show, is this equal to? On the right side, you substitute 1 for n, so 1 times n, 1 times 1 plus 1. We simplify both sides completely and see if we end up with a true statement. Left side is already simplified, so we focus on the right side. We do order of operations. 1 plus 1 is 2, right there. Is 2 equal to 1 times 2 is 2. Is 2 equal to 2? Absolutely. So this basically shows us that the base case is true. Alright, so we have the foundation. The foundation checks out. So now we're going to advance to the next level. All right. Just a side note, something to keep in mind is that the base case, we mentioned this earlier, is not always S sub 1. You got to read the problem carefully to see what the base case is so you don't end up with a wrong foundation. Okay, so base case done. We're going to move on to step number 2, check, which is the inductive hypothesis. All right, so for the inductive hypothesis, we are going to make an assumption. All right, we just pick an arbitrary k and assume that it's true. All right, so assume that S of k is true for some integer k in the set of positive integers. All right, so we're gonna write down, if that's it, if S of k is true, then what statement are we assuming is true is a question. What statement are we assuming is true? So this is what we're going to assume is true based on S of k being true. So we're going to do the following. We're going to assume that S of k. What on earth is S of k? Well, to get what S of k is, what we're going to do is basically substitute k into this original statement. You see what S of n is? All these, you see the spots with the n's? We're going to replace those n's with what? K's. All right? So we're going to assume that 2 plus 4 plus 6 plus pattern goes on, right? Instead of even numbers, all the way to 2, instead of n, 2k. We're going to assume that this is equal to k times the quantity k plus 1 for some positive integer some positive integer k. Okay? Positive integer k. Another way you can say this in condensed notation is k in the set of natural numbers for some k in n. All right? So now this is our inductive hypothesis. We're going to assume that this statement is true. All right? The inductive hypothesis step is just making an assumption that the statement holds for some arbitrary positive integer. Okay? Now we're going to move on to the inductive step. All right, so inductive step. We're trying to show if a domino effect applies. If you pick any k, does that automatically imply that the next step is true? So in this inductive step, we're going to show that S of k is true based on the assumption follows that S of k is also true. And then in that way, we can apply it to the set of all positive integers. All right? So let's go ahead and carry out that process. Now, in the entire inductive proofs process, the inductive step is normally the longest one and most involved. So there you have it. Okay, so for our inductive step, we're going to start with the statement S sub k plus 1. So what is S sub k plus 1? Notice that the index is now k plus 1. So all we're going to do here is we're going to advance this particular statement to the next integer value. Okay? So we're going to replace it with k and then advance it by 1. So we have 2 plus 4 plus 6 plus plus S sub k. All right, this is S sub k. All right? Yeah, I forgot to put S sub k. So let's put S sub k right here. Bam. So this is S sub k. So that's S sub k that we had before. We're going to assume that that's true. So here is S sub k. Now we're going to advance it by an additional value. So that's simply going to be 2 plus, you replace k with k plus 1. All right, so that's the next term in the sequence. All right, now that we have this, what is this equal to? So we're going to go ahead and take a look at this statement right here and see, can we make a substitution using our inductive hypothesis. All right, from our inductive hypothesis, we know that this component right here, from 2 all the way to 2k plus 1, we know that it's true based on our assumption. All right, so we can make a substitution here. So this whole statement is equal to, replace that piece with the right side of the inductive hypothesis, this part right here. Okay, so we'll make that substitution. We're going to have k times the quantity k plus 1. All right, and then we'll bring down the right side of the equation plus the next value, 2 times k plus 1. All right, we can write this based on the assumption that we had. We made an inductive hypothesis. All right, so now we're going to simplify this and see if we can reduce this into this, the right side of this statement, but it's replaced with n plus 1. All right, or k plus 1. So in order for us to do this, it's easier to do this if you know your destination, you know your end goal. What are we looking for? What do we want our results to look like? All right, so this is what we want it to look like. So look at this right side here. We're going to replace these variables with k plus 1. That's what our desired intention is. All right, if we go all the way to 2k plus 1, we want these to be replaced with k plus 1 also. All right, so you see what we have on this right here on the left side. You see how this value is k plus 1. We want these to be k plus 1s also. Okay, so what on earth am I talking about? Let's see what that looks like. So on the left side right here, I'm gonna make a little scratch work. This is not part of the proof. This is just to give me a clear direction as to where I'm going. Okay, I want it to be, instead of n times n plus 1, it's going to be k plus 1 times the quantity k plus 1 plus 1. This is my goal right here. If you have your goal clearly set in mind, then it's easier to work your way there. All right. Okay, so how about I simplify my goal a little bit to a form where I'm basically working backwards, where I can easily convert this into this statement. Okay, it's easier sometimes to simplify your goal a little bit more so you can work from your right side to your intended goal. So let's do that. So if I simplify this, I have k plus 1, and then the right factor is k plus 1 plus 1. Okay, multiply that out. Add that. You have k plus 2. And it can, well, we could just leave it right here. All right, we want to get k plus 1 times k plus 2. If I can get this one up to this point right here, then I can just simply work my way up to the top. All right, kind of reverse engineering. Okay, let's do it. So on the right side here, we're going to expand k squared plus k just by distributing the k across these two terms. Bam, bam. Plus distribute the 2 also. Bam, bam. You have 2k plus 2. Keep your eye on the goal. All right. So we have 4 terms here. We can factor by grouping, right? From the first 2, we can factor out k plus 1. And then in the second term, factor out 2k plus 1. And then you have factor out k plus 1, right? These 2 identical factors here, you factor them out. And then you're left with k plus 2. Bam, bam. Put it together as own little parentheses, group in. Oh, beautiful. That's exactly what we want. We're in this part. You are here now. So it's easy for us to just work our way up to the desired goal just by rewriting this piece, this 2, we'll break it up, and then group the k with one of the addends, which is 1, and then we're done. Okay, so it's going to become k plus 1 times k, instead of 2, you write it as 1 plus 1. Right, the goal is we want to group these 2k plus 1s together. So when we group them together, we're going to have the desired state, which is k plus 1 times the quantity k plus 1. All right, is an associative property of addition. Associate those two. Bam, that's exactly what we want. All right, so by advancing to 2 times the quantity k plus 1, we ended up with a situation where s sub k had the right side, all the k's were replaced with k plus 1. This is exactly what we want. All right, so our goal, we can go ahead and erase that. That's just scratch work. It's just to help us to see where we were going. And then now we can say the significance of this statement. This statement shows that the assumption s of k being true automatically follows that the next step, s of k plus 1, is also true. Magnificent. So let's go ahead and write down our concluding statement. What can we conclude based on this? We can conclude that the statement so let's write conclusion. The statement s sub n, which is that 2 plus 4 plus 6 plus all the way to 2n, is equal to n times n plus 1. This statement right here is true for all positive integer n. All right, put your nice little box of accomplishment, and there you have it. Okay, if you have any questions about any part of this presentation, specify in the comment section below. We'll be glad to assist you. Thanks again for taking the time to watch this presentation. Tons of support resources can be found in the links in the description below, or just go to mathgotserved.com on the pre-calc, the induction section. And we will see you in the next video. Take care and goodbye.